Now we are going to solve some problem of definite integration, which will make our problems very easy. So theorem 3.1, if f is continuous on 0 to a closed interval, then 0 to a f of x dx is equal to 0 to a f of a minus x dx. That is, limit minus variable gives the same value as we get in the original function. So, the proof of the theorem is let I is equal to 0 to a f of x dx. So let x is equal to a minus t. So dx is equal to minus dt. Now by method of substitution, x is equal to gt must be a monotonic function. So is monotonic decreasing? As it varying from 0 to a. It is clear from this a minus something, as the value of a increases, value of x decreases. And also dx over dt is equal to minus 1, that is a constant function. Constant function is always continuous. So is continuous function in open interval 0 to a. Also we have to find the value of alpha and beta. When x is equal to 0, t is equal to a, and when x is equal to a, t is equal to 0. So by method of substitution, I becomes a to 0 f of a minus t minus dt. So we get minus of a to 0 f of a minus t dt. Also we know that a to b f of x dx is equal to minus b to a f of x dx. So using this rule we will get I is equal to 0 to a f of a minus t dt. And also we know that on changing the variable, that is a to b, f of x dx is also equal to a to b f of t dt. So by using this rule, we get I is equal to 0 to a f of a minus x dx. So we will get from this 0 to a f of x dx is equal to 0 to a f of a minus x dx. That was our first theorem. We will use this theorem in the given problem. Now on the basis of this theorem, how can we apply this theorem in the problem? Let's see. For example, we have I is equal to 0 to 2 pi cos cube x sin raised to power 5x dx. So we are applying here a is 2 pi. So we are going to apply f of a minus x. So we are replacing x by a minus x, and here also a minus x. It becomes f of a minus x. As we know that cos of 2 pi minus x, that is 2 pi minus x lying fourth quadrant, cos is positive and sin is negative. So we get I is equal to minus of 0 to 2 pi cos cube x into sin raised to power 5x dx, as sine of 2 pi minus theta is minus sine theta and cos of 2 pi minus theta is equal to cos theta. By using this, we get I is equal to this. So we get minus of 0 to 2 pi cos cube x sine raised to power 5x dx, that is minus of I. That is, we get I is equal to minus of I. That implies 2I is equal to 0. That implies I is equal to 0. That is, we get the value of integral, that is 0 to 2 pi cos cube x sine raised to power 5x dx is equal to 0. So if we use simple integration by parts in the definite integral, we will get the same result. You can verify it very easily if you want to do it. Now the next theorem is theorem 3.2. It says that if f is continuous over closed interval a to b, then a to b f of x dx is equal to a to b f of a plus b minus x dx. If we see, this is also in the form of theorem 3.1. As we put 0 is equal to a here and b is equal to a, we will get the same result as we get in theorem 3.1. So let's see how can we solve it. We will solve it in the similar manner as we done in theorem 3.1. So the proof is, let I is equal to a to b f of x dx. Let x is equal to a plus b minus t. That gives dx is equal to minus dt. And as x is equal to a plus b minus t is decreasing in a to b and it is continuous in open interval a to b. Therefore, we have to find the value of alpha and beta, and also its derivative dx over dt is equal to minus 1 is continuous in a to b open interval. Now we have to find alpha and beta when x is equal to a, t is equal to b, and when x is equal to b, t is equal to a. So by using all these substitution, we get I is equal to b to a f of a plus b minus t into minus dt. So we get here minus of b to a f of a plus b minus t dt. So as we know the rule, if we change the place of limit, negative sign will be eliminated. That is, a to b f of x dx is equal to minus b to a f of x dx. So by using this rule, we get I is equal to a to b f of a plus b minus t dt. Also, we know that on changing the variable, there is no difference in the integration. So we have the rule a to b f of x dx is equal to a to b f of t dt. So here, by using this rule, we get I is equal to a to b f of a plus b minus x d of x. So I is equal to, that is a to b, f of x dx is also equal to a to b f of a plus b minus x dx. That is our result, that is stated in theorem 3.2. So we will do an example on the basis of this problem. This theorem, that is, for example, evaluate I, that is ranging from 1 to 2, under root x over under root 3 minus x plus under root x. This theorem is used mainly where we have in the denominator the function, that is a sum minus x, that is a plus b minus x form also there. When we replace this part by this, we will get the required result. How we can done it? We are applying the theorem. So I become 1 to 2 a plus b minus x, that is a plus b minus x plus a plus b minus x. So we get I as 1 to 2 c minus x, that is under root x plus c minus x dx. So by adding these 2's, we get 2i is equal to 1 to 2, that is given by number 2, and in the starting I, that is number 1. So by adding these 2i, we get under root x plus under root c minus x over under root x plus under root c minus x dx. So you can see that denominator and numerator become same. So by using this theorem, we will get the solution of such type of problem very easily. So from here we get, that is x, that is ranging from 1 to 2. So we get 2i is equal to 2 minus 1. So we get I is equal to 1 over 2. So the value of that integral by using the theorem 3.2 we get, that is half.